My name is Weltz, and I'm one of Alison's lucky students that was allowed to work on data which had been collected over a long period of time. I think I might have been one of the students to harass her actually for this project, but
persistence.
Persistence, exactly. With my background in zoology and working on various terrestrial species and marine mammals, I actually wanted a project which was something which had a vertebra and something that was applied in management. And so this was a great project for me. So the project focused on looking at the relationship between environmental variables and shark sightings or presence along False Bay beaches. And it was in collaboration with Alison, with Professor Colin, Dr. Henning and Monwabisi from Shark Spotters. So to start off, I'd just like to touch a bit on the relevance and importance of such a study. So identifying the habitat use and movement of larger species in the marine environment has actually been studied since the 1920s. And researchers use this information to understand how they interact with each other, how they interact with the environment, and ultimately play a role in ecosystem functioning. It also allows us to understand and minimize human-animal conflicts in these areas. And shark encounters are a definite human and animal conflict in the Cape Peninsula. So as we've heard others speak before, that the shark attacks have been increasing globally, and particularly in the Cape Peninsula itself since the 1960s onwards, we've seen an increase in shark attacks and also fatal shark attacks. So, Also, the shark attacks in themselves attract a lot of attention and media, and therefore have very negative effects on public perception and can negatively affect not only the economy of the areas in which these attacks occur, but also conservation of the species. So it's really important to understand more about these issues. So there have been various mitigation methods in order to try and minimize these conflict areas, such as we've heard before, gill netting, perhaps drum lining, or even looking at some kind of electrical shark shields. Some of them less intrusive, others more intrusive. A lot of them very detrimental to the environment, as well as financially detrimental to the economy. So in about 2004, Shark Spotters was implemented in False Bay as a non-intrusive method to try and mitigate this issue. And how it functions, or how it works, is it's based on a flag warning system where 2 shark spotters are allocated to a spotting beach. One is situated on an elevated mountainside from a viewpoint, the other on the beach. Both are in contact with radios and have polarized sunglasses. And should the spotter on the elevated mountainside sight a shark in the area of the swimmers or the water users, he will alert the shark spotter on the beach, who will then sound a siren and raise the appropriate flag to actually encourage the water users to exit the water. So to try and minimize that encountering. And in order to minimize spotting fatigue, shark spotters are divided into spotting shifts, morning and afternoon shifts, and summer generally from about 7 till 1 o'clock and 1 o'clock till 7 o'clock in the evening. And not only do they try and warn water users of the presence of white sharks and get them to evacuate the water, they also collect very valuable information on the shark sightings. So when it was sighted, how long it was sighted, the tracks of where it was going. So a lot of valuable data on these data sheets that have been provided. Okay, so Alright, so the aim of this study was to use this data collected by the shark spotters to actually investigate a relationship between the probability of shark sightings per shift at beaches in False Bay in relation to environmental factors such as sea surface temperature at the time, lunar phase, wind patterns such as wind speed and wind direction, as well as looking at a yearly trend of these sightings along those beaches. And this study was conducted over the years 2006 to 2011. And because it's difficult to distinguish whether a shark sighted by the shark spotters was the same shark or if it was different sharks coming and going, instead of looking at the amount of sharks, we actually took a binomial approach and used the actual probability of sharks. So just a bit to touch on the shark sightings data itself. This study focused, there are 7, I think it's 7 now, right, Alison, beaches which are in the shark spotters, or have shark, is it 8 now? Okay, so there are 8 beaches now which have shark spotters allocated to them. But this study focused particularly on Muizenberg and Fish Hoek because they have the most sightings over the study years, so the best quality data. And they also have the highest risk of encounters and have had the highest risk of shark encounters over the years. So to give you an idea, this is the mean number of white sharks per shift across all the months of the year for all the study years. And as you can see, there's a very clear seasonal trend with increased shark sightings around about autumn, spring, and summer, particularly summer months, with very, very few sightings and poor sighting conditions in June, July, and August, so in the winter months. And this has actually been confirmed by a recently published study by Carcharodon in 2013, earlier this year, which showed that using acoustic tagging, that white sharks spend most of their time around Seal Island in winter months feeding on weaned pups, and then tend to have a dietary shift towards more elasmobranch and larger fish species, which move into the area closer inshore in summer months. So therefore we excluded the winter months from the study to focus more on the summer months when they actually are inshore for sighting. Because sightings data is very much dependent on the individual ability of the individual spotter, we chose to filter our data according to only include spotters which have done over 100 spotting shifts at the designated beach. And we also included spotter as a random effect into our analysis to actually incorporate this. So our environmental data was externally sourced. We got the sea surface temperatures from the South African Weather Services and was provided in daily measurements from degrees Celsius by a handheld thermometer. Our lunar phase was provided by the South African Hydrographics Unit, and we divided it into 8 phases. So you have your common 4 phases, your full moon, third quarter, new moon, and first quarter, and we divided this into further subsequent 8 phases within that. The wind speed was measured at the International Airport of Cape Town in kilometers per hour, which has been said to be the best representative for wind speeds in False Bay. And the wind direction was provided in degrees and was therefore categorized into 4 categories, namely onshore, offshore, cross-shore, and longshore for each beach individually. And both the wind data was provided by the South African Weather Service as well. So in order to first touch on this data, we wanted to make sure that we had a consistent unit throughout our study, and we chose spotting shifts, so the morning and afternoon shifts, as I've mentioned, we chose as our unit. So all of our environmental data was averaged for each shift, and our shark sightings allocated to these shifts. For the data analysis, we wanted to see, using Cleveland dot plots and box plots, whether the spread of the environmental variables over all the months of the year was a good spread, even when we took the winter months out, which it still showed. And we also used multi-panel scatter plots in order to identify any collinearity between these variables, which there was none, and there were no outliers, so therefore all the mentioned variables here were included in the study. So in order to investigate the relationship between these environmental variables and our shark sightings, we used a statistical model known as a GAMM, which is a general additive mixed model. And it is similar to our generalized linear models, but it is less restrictive to the underlying data. And our data, particularly our shark sightings data, had a lot of zeros. So we had very normally distributed data. So, and generalized additive models are great for non-parametric data because they actually they replace the least squares with smoothing splines, which allows the model to better fit your data, which is non-parametric. So this is the model our final model for both our beaches. And the logit function denotes the binomial link function, with P being the probability of sighting a shark at each beach. The year, sea surface temperature, lunar phase, wind speed, and wind direction and shift were our explanatory variables. We added in shift as looking at time of day, so whether morning or afternoon shifts, if there was a difference in affecting the probability of shark sightings, and alpha being our random effect of the spotters, which had been included. All our F's shown here are our thin plate regression splines, which we use as our smoothing functions in this model. So in order to get our full model for both beaches, Muizenberg and Fish Hoek, we first included our random effect of the spotter into both models to see whether it was significant, which it was, so therefore we left it in both models. And to find the optimal combination of each one of these explanatory variables to our link function, we use the Cake's information criterion, with the lowest Cake information value indicating the best combination of explanatory variables. Therefore, thereafter we used sequential F-tests to actually test the significance of each one of these explanatory variables and how that might affect the probability of sighting a shark. And we actually took it a step further and actually using this model to predict the best optimal times and probabilities of sighting sharks at both beaches. And all of this was done in the MGCB package in R. So our results. The sea surface temperature was highly significant for both Muizenberg and Fish Hoek, so showing very similar trends with increased probability of sightings towards 18 degrees Celsius, with a peak around 18 to 20, and thereafter it then stabilizes. And our model predicted up to 8 times higher chance of sighting a white shark at 18 degrees in comparison to, for example, 14 degrees at Muizenberg. Our reasons for finding this trend, there were 2 options in our mind. It was either, it's the physiology of the white sharks themselves, so their own preferences for these temperatures, or it's their prey. And white sharks have a very wide tolerance range in terms of temperatures, from about 0.5 degrees Celsius in Alaska all the way up to 22 degrees Celsius in California. So it's very unlikely that they're going to be limited to such a narrow range by their own tolerances. They're also able to increase their internal body temperatures by up to 15 degrees in comparison to the external temperatures. So again, very unlikely. So we turned to their prey to see if we could find any answers there. And we found that white sharks in summer, as shown, have a dietary shift towards more lasmobranch and fish species which move into false bay in these times. Dusky sharks, for example, are known to migrate down from KwaZulu-Natal to escape the warm waters up there. And white zebras also spend a lot of time in summer inshore. And these are very common prey species. These are just a couple that I've mentioned, but we've actually found a whole list of prey species from white sharks which show very similar temperature ranges in this time in False Bay. So we're quite certain that it's the temperatures of its prey and their preferences which is ultimately determining the preference of white sharks around this time. Our second most significant variable was lunar phase, and we found that for both Muizenberg and Fish Hoek, new moon was the highest probability of sighting white sharks, 4, 5, 6 being here, down here, 4, 5, and 6 around new moon, and the lowest probability at full moon. And our model predicted up to 4 times higher chance of sighting a shark during new moon at Fish Hoek in comparison to full moon. Now, moon phase is known to provide very predictable patterns in the marine environment, which have a great effect on all behavioral functions of marine organisms, such as reproduction or migration or aggregation. And it has actually been shown in various other studies, one in False Bay, looking at seal colonies, which showed an increase in success of predation rates around new moon. In California, where they said that it was the camouflaging of the white sharks during low light intensities which allowed them to better have hunting success on their northern elephant seal prey. Or even in Australia, they've shown that great white catches in nets closer inshore of juveniles was again higher at new moon in comparison to other moon phases. So there are other studies out there to support our findings. So we do, although the mechanisms in False Bay itself are not known as to why we're finding this trend, we think it's most likely due to hunting strategies or increased hunting advantages and movement of increased food availability into that area during new moon. Our third most significant variable was the trend in year, and we found that there was, for both Muizenberg and Fish Hoek, around 2009, 2010, an increase in shark sightings. We did investigate whether there was a change in temperature over these years, and we found that there was no significant difference in water temperature between any of our years. So the water temperature stayed relatively the same. But reasons for actually finding this recent increase may either be due to an increase in the actual population numbers of white sharks in False Bay. And as Alison mentioned earlier, Adrian is actually doing a population estimate at the moment, so it'll be quite interesting to see those results. Or it could also, because they've been protected by law for the last couple of years, so it would seem to make sense. Or it could be one individual shark which is just using that area more frequently, or it could be other sharks moving into the area or into False Bay over time. So although it's not really known why we're seeing this increase, it just highlights another need for more research into this area. Our wind patterns, wind speed and direction, were not significant for either Muizenberg or Fish Hoek in our model. And although this seems strange, we understand that it is most likely due to a lag effect, which we did not include in our model. So what happens in False Bay is we have the southeasterly winds which blow really strong throughout the summer and a couple of days in a row, and then they track warm water along the coastline, which leads to algal blooms and increased fish movement into the area. But this is usually a lag effect, so it usually takes a couple of days for this to actually come into effect. And we didn't include the lag effect into our model because it overcomplexes the model. And the GAMM actually really struggles to separate the effects of each individual term when it becomes too overly complex by including interaction terms and all sorts of lag effects. So this might be something which could be looked at as a whole separate project. Spotting shift or time of day, we found only significant for Fish Hoek, which was 60% higher chance of, or probability of sighting sharks at Fish Hoek during the afternoon shift, which I found was quite interesting now, having heard Jeremy's talk. But we perhaps, because we're not quite sure about the actual behavioral mechanisms in Fish Hoek yet, and more data needs to come in on their movement here, but it might also be due to geographic positioning of the beach itself. So Muizenberg and Fish Hoek are situated differently geographically, and the viewing angle from Fish Hoek's spotting point is northerly, which is where the sun rises. So it might struggle with glare in the morning and that kind of stuff. But I think what would be quite nice would be actually, because this is a very purely quantitative study, and it would actually be nice to almost do a qualitative study as well with the shark spotters to almost understand, what are they seeing in those moments, or how are they struggling to capture data in those times. So this might be another thing that could be expanded. So how is a study like this put into management and applied? Shark spotters have communicated the outcomes from sea surface temperature and lunar phase to the public through various media. It's too early to tell whether bather awareness has been changed through such an outcome, but bather numbers are being recorded by shark spotters, and continuous monitoring and implementation of this model in the future, as well as bathing numbers, could maybe show how such an approach to conservation and research might affect bather awareness in the long run. And as I mentioned, there are various other variables which could be included into the model in the future, perhaps qualitative research. In terms of quantitative research, other variables such as trek netting or other animal activity in the bay could be included and investigate if there's a relationship there. For the moon phase in particular, maybe even the water temperature, it might be interesting to have a look at the actual, what is the prey doing, and actually do some studies on the actual prey of the white sharks to see why they're using these areas more at this time. So these are all avenues which I think this project provided a really great base for. So yeah, and I think any knowledge on the movement of larger shark species within very popular bathing beaches in anywhere in the world really is a great advantage to try to minimize any kind of conflict of human-animal interaction and try to actually prevent any repercussions negative in terms of economy as well as conservation.